Good morning, gang. Today is another fun and exciting day in the land of calculus. We are going to meet our first few tricks for differentiation. So let me get QCamera fired up here and we can get moving. I would not mind beginning today with a homework question or two if there are any, since the concepts we covered over the last few classes have been such important concepts. I really do want to make sure that you guys are as comfy as can be with them. So is there a particular homework problem or two that you guys have been banging your heads against the wall on, or just really want to see discussed a little bit, something like that?
I have one. I just need to get logged into my account.
Let's see here. So I can pull it up.
Like number 3 or 4.
Every time. So we want to look at, you said 3 or 4?
Yeah, number 3.
Let's see. From homework 2?
No, homework 3.
Homework 3. Okay, and which one?
Yeah, there you go, number 3.
Number 3 up here, this guy? All right, so this one's not too bad here. We just need to calculate the derivative at that point. And it's going to require some factoring. So the factoring can be a little tricky. Watch out. So let me write this down. Homework 3, problem 3, find the equation of the tangent line to y equals x cubed minus 3x plus 1 at the point 4, 53. So we need two things, of course, right? We need our point, and that's this thing, and we need the slope. My function in question here is this guy. So my slope here is going to be f primed of 4, which is going to be the limit as h goes to 0, f of 4 plus h minus f of 4 all over h. Although, as we were talking last week, we could calculate this in general. We could calculate f primed of x and then plug in 4 for x in that expression. But I think this will be easier since we just want the one slope. So we do need to figure out f of 4, and we will need to write down f of 4 plus h in terms of this expression here. F of 4 is 53, right? The point of tangency here, you know this is the point a comma f of a. So we know that this guy right here, f of 4 is 53. And then f of 4 plus h, that's going to be a little bit complicated, but we'll write it down and then we'll deal with it. So that's f of 4 plus h is going to be 4 plus h cubed minus 3 times 4 plus h plus 1. All right, here's f of 4 plus h minus f of 4 itself is 53. You could compute that by plugging 4 in here and crunching it out, but there's no reason to because they gave it to us here. And then downstairs we just have h. Good so far?
Where did you, okay, so why did you plug in 4 plus h cubed?
Well, look at the previous one. All right, this is the definition of f primed of 4.
Yep.
F of 4 plus h is what you get by plugging 4 plus h in for x. Just like f of 4 is what you get by plugging 4 in for x.
Okay.
So it's just following the definition, following the function notation here. Now we do have a meaningful bit of work to do when it comes to cleaning this up. The algebra here is not as as nice as it could possibly be. There's a trick for expanding things like this. Let's see if I've got some space here to scribble. You guys familiar with Pascal's triangle? The way I'm generating this is I start with ones at the top, right? 1, 1, 1. And then in the next row, I add the two things above. So it always starts with a 1 on the far side. And then I get the 2 in the middle here by adding the 1 and 1 there. And then it ends with the 1. So to get the row beneath, I'll start with the 1. And then this 3 is going to come from 1 plus 2. This 3 comes from 2 plus 1, this one. This is called Pascal's triangle. And it's a trick for expanding binomials. So that third row tells me that x plus y cubed, this row right here, is x cubed plus 3x squared y plus 3xy squared plus 1 times y cubed. These are called binomial coefficients. So it's just a trick for expanding things like this 4 plus h cubed here. So that 4 plus h cubed, according to Pascal's triangle, will expand as 4 cubed plus 3 copies of 4 squared times h. So I should write this like this. Plus 3 copies of 4 times h squared plus 1 copy of h cubed. That's the 4 plus h all cubed. And then this piece, I'll distribute my -3. I'll have minus 3 times 4 minus 3h. And then I've got plus 1 minus 53. All over h. Now you don't have to use Pascal's triangle there if you don't want to. You can just, FOIL this out. You just have to multiply 4 plus h times 4 plus h times 4 plus h. It'll take longer. So this is a faster path to do that. And then these terms, I just distributed the -3 here. The plus 1 is the plus 1, and the minus 53 is the minus 53. All right, so what can we do here? Let's clean things up. 4 cubed is 4 times 4 times 4 is 16 times 4 is 64. So this is lim h0, 64 minus 4 squared is 16. 3 times 16, let's see, what is that? That's 3 times 30 plus 3 times 6, that's 48, right? 48h, is that correct? 3 times 16, yeah. And then 3 times 4 is 12, so plus 12h squared, and then plus h cubed, minus 3 times 4 is minus 12, minus 3h, and then -53 plus 1 is minus 52. All of this is over h. So let's combine our constant terms. I've got a 64 here.
I have a quick question. Why is it 64 minus 48h? Because in the line above it's 4. Is that 4 cubed plus?
Yeah, sorry, no, you're correct. You're correct. This is a plus,
okay.
So this should be a plus. Yeah, thank you.
Okay. Thanks.
No, you're 100% correct. Yeah, all right. So let's combine our like terms. The constants I'm actually expecting will go away. So let's look at the constants first. If you take 64 and you subtract 12, that gives you 52. 52 minus 52 is 0. So indeed, if you take this, this, and this, they all add up to 0. And that's the nice sauce here, because that will let me factor an h out from everything that's left. Now let's see, what can I combine among the things that are left? I have an h cubed, just one of those. I have a 12h squared. I have a plus 48h and a minus 3h. That'll give me a plus 45h. And that's everybody, right? All that is over h. So those terms combined, and this term combined with this term. I can factor in h from the top. Cancel with the h from the bottom. I'm going to get limit h to 0. Let's see what's left. H squared plus 12h plus 45. And that's all over 1. You can write the over 1 downstairs if you want to. I'm not going to. You don't need to. As h goes to 0, h squared goes to 0, and 12h goes to 0. So out of this, we're just going to get 45. So the slope of my tangent line is 45. And now I've got my point and my slope. So I'm ready to write down the equation of this tangent line. Y minus 53, my y value on the line, equals m 45 times x minus the x value that I know is on my line. There it is. And you can leave it like this. So this is a classic problem. Problems of this sort absolutely will show up on test 1. There are some challenges here that aren't in all of our problems. There's some unique challenges to this, like cubing out the 4 plus h, right? When we saw Pascal's triangle was useful there. Pascal's triangle and the binomial theorem are very useful things. In fact, we're going to use them today in a proof. But I'll come to that in a little bit. Other questions?
Professor, yeah. I have a question.
Sure, Adrian.
So in the homework, we've been doing a lot of like the application of the concepts. We haven't really been tested on the concept. We haven't had questions on concepts. Are there going to be some questions in the tests or the exams that are going to be like on the concepts?
So the sort of questions I can ask you are a little bit limited, especially in WebAssign. You know, so like, tell me what it means geometrically is a sort of question that's a little bit hard to ask in WebAssign. Can you be a little more specific? So what sort of concept questions are you wondering about? Most of this is calculation, right? But certainly problems like these are very concept driven. If you want to answer when is the particle moving to the right or to the left, you have to understand how to interpret this position versus time graph. And then sketching the velocity function. I think some of these are pretty concept heavy, but it depends on what you mean. So can you give me an example of what you're thinking of as a concept type question?
Right, so maybe something more along the lines of like the concept of a derivative, like what that can do to certain problems. Like you can go from average rate of change, like instantaneous rate of change, and from, I believe it was like speed, velocity, and then something else, like questions like that that are more, that aren't as much, you're given a problem, you insert numbers and solve, more like
there
you
will
have to
be
think
some
about
problems.
it.
Yeah, there will be some problems of that nature on the test. And as we get a little bit deeper into understanding what the derivative is, I'll be able to include some homework questions like that. But you're right in saying that there are kind of limitations in this online homework setting to the types of problems I can ask you. But there certainly will be problems that prep you for this concept of instantaneous rate of change versus average rate of change. And definitely things having to do with continuity and differentiability, like we were talking about in class last Friday, like whether a function is or is not differentiable at a point. Those sort of concept questions will show up on the test. Let me see here. So there was another question in chat here. Joe's asking, where did the cube come from? So our function here was x cubed minus 3x plus 1. So f of 4 plus h is what you get by subbing in 4 plus h for x everywhere here, right? This is f of x. So if you take x cubed minus 3x plus 1, and everywhere there's an x, you write 4 plus h instead, and you get 4 plus h cubed minus 3 times 4 plus h plus 1. So this piece right here this is f of 4 plus h, and this piece is f of 4. So the cube came from there.
All right, I got that.
And then, Adrian, I can try to include some more concept-focused questions in the homework, but there is a small limitation to what we can do through WebAssign. If you look in the textbook, and I always encourage you guys, it's a really, really good habit to be in, to look in the textbook and solve extra problems. The homework that I put up in WebAssign really should be treated as the bare minimum that you can do to survive in this class. But if you come in here and look at some of these, especially sections 2.7 and 2.8, you will find plenty of concept questions about rates of change and things like that. Specifically down here. So if you're interested in instantaneous rates of change versus average rates of change, we talked a little bit about this last week, and we will talk more about it as we move forwards and get into some of the application problems. But working some of these extra examples and some of the extra problems in the textbook might help if you're feeling a little nervous there. Or if you just want to talk about that stuff more, come by an office hour. I'd be happy to have a lengthy chat with you about the different interpretations of the derivative. Any other questions before I move on?
Do you think you could do number 6 on my homework?
Let's take a look. Displacement is given by 4 over t squared. Find the velocity at these different times. Sure. Just to be clear, number 5 is one that I want you guys to spend some time on. I was expecting you guys to ask for this problem. If everybody's really comfy with this, I won't burn class time on it. But do invest some time in number 5 and number 7 here. These are both meant to get you thinking deeply about the concepts. But I would be happy to go through number 6. After that, we are going to have to move into the new material for today. Mackenzie asked, why is it all open points? Like open intervals?
Yes, on number 5.
If we're talking about intervals of increase and decrease, those are open. So for example, right here at the point 1, 5, this function is no longer increasing. It increases everywhere from 0 to 1, but then right here at x equals 1 or at t equals 1, sorry, it ceases to increase. We can talk a little bit more about this, but if you go back to the very first few lectures in this class, we talked about open intervals and closed intervals and kind of the meaning of the topology of the line. This is getting at that. This function is no longer increasing at time t equals 1. It's only increasing from 0 to 1. And then at 1, it changes. It starts doing something else. It becomes a constant function. So open intervals are the most natural way to describe that increasing and decreasing behavior, which happens to be the exact answer to like moving to the right and moving to the left.
Thank you.
Yeah, of course, of course. All right, so we want to look at number 6, and they tell us that the displacement function is 4 over t squared. They tell me a particle is moving along a straight path. This is homework 3, number 6. A particle is moving along a straight path with displacement function and S of t is equal to 4 over t squared. There's kind of two common notations here, by the way. When we introduced the displacement or position function, we called it x of t. S of t is the other common notation. Both you'll see. They want us to find the instantaneous velocity, right? So find velocity at times t equals a, t equals 1, t equals 2, and t equals 3. Okay. So this function, s of t equals 4 over t squared, this tells you where the thing is, right? At time t equals 1, its position is 4 over 1 squared, or 4 meters. At time t equals 2, the position is 4 over 2 squared, or 1, right? 4 over 4 meters. At time t equals 3 seconds, the position is 4 over 9, or a little bit less than 1/2. So this particle is retreating, right? The graph of s of t. Remember, we played a little bit with these things. The graph of s of t here actually looks like this. At time t equals 1, we're up here at 4. At time t equals 2, we're down at 1. It's not quite to scale. And at time t equals 3, we would be down here at 4/9. So what's going on here? If you imagine this particle as a little dude walking back and forth along a track, time t equals 1, he's over here, and his position is decreasing, which means he's going to the left. Let me see, actually, I think for you guys, what was I doing? I was putting times up here and positions down here. So we can say this is at 4 meters. Time t equals 2, he's come back a little bit to 1 meter. So I'll call this over here 0 meters. Here's 1 meter. Or maybe I'll call this one the 4/9. I'll call this one 1 meter. So my dude is walking right to left. This is time t equals 2. This is time t equals 3. So he's walking from here to here to here. So he's walking right to left, and he's going slower, right? That's the graph kind of becoming more shallow. At time t equals 1, he's 4 meters from the origin. At time t equals 2, he's 1 meter from the origin. At time t equals 3, he's about a 1/2 meter, or 4/9 meters from the origin. So he's walking right to left, and he's slowing down as he gets closer and closer to the origin, to the starting point here. They want the velocity, which corresponds to the slope of the tangent line here, here, and here. And they asked us to cook up the velocity at time t equals a, where a is just an arbitrary constant. And then if we do this first, we can plug in 1, 2, and 3 for a to get the answers to the other parts. So the smart thing to do here is to calculate the velocity at time t equals a, and then use that to cook up the velocities at these other times. We know that v of a is s primed of a, right? This is the relationship between velocity and position that we discussed last time. that the derivative of position is your velocity. And by definition, s primed of a is the limit as h goes to 0, s of a plus h minus s of a all over h. So this is how we get started.
I have a quick question, or more of a comment. I think I found an easier way to find derivatives.
There are lots of tricks, yes. There are lots and lots of easier ways to find derivatives. And the main point of today's lecture, we haven't gotten to it yet, is the first one of those tricks. But all of chapter 3 is going to be easier ways to find derivatives. There's a reason I segment the homework like this. I want you guys doing these problems the hard way, right, through limit definitions. But yes, there certainly are. If you start noticing patterns between the power here and the power in the derivative, there are very nice relationships.
Yeah.
So let's move quickly through this so I can prove that result for you, and then you can use that freely in all the homeworks after this. I am excited to see if what I'm going to prove for you today is the thing that you've discovered. It's always really great when you guys discover new mathematics. But let's go ahead and knock this one out. So s of a plus h is going to be 4 over a plus h quantity squared minus s of a is 4 over a squared. And all of this is divided by h. We need to have a common denominator between the two fractions upstairs. So I'll multiply this by a squared over a squared and get 4a squared over a squared times a plus h squared. Minus, I'll multiply this by a plus h squared over a plus h squared, and I'll get 4a plus h squared over a squared times a plus h squared. And all of this is still being divided by h. Now in my next line, I'll have lim h to 0. I'm ready to put those two fractions together. Upstairs here, I'll have 4a squared minus 4a plus h quantity squared. All of that is being divided by a squared times a plus h squared. And to get rid of that h from the bottom, I'm going to just write this as multiplied by 1 over h. Right? Dividing by h is the same as multiplying by 1 over h. We might as well have this stuff. Carrying on, we have lim h to 0. Numerator here is 4a squared minus 4 times a squared plus 2ah plus h squared all over this denominator, which is a squared times a plus h squared. And then I'll bring this 1 over h in. He'll give a factor of h downstairs like this. I need to distribute this 4. Right? It's a negative 4, so I'm going to distribute a negative 4 across these terms, then combine like terms and see if I can factor and cancel anything. So I'll get lim h to 0, 4a squared minus 4a squared minus 8ah minus 4h squared over a squared times a plus h squared times h. The 4a squareds go, and we get lim h to 0, negative 8ah minus 4h squared over a squared a plus h squared times h. And we can factor in h, cancel at the bottom. The h's go, this h and this h. And what's left is then h to 0, negative 8a minus 4h all over a squared times a plus h squared. Now that this factor of h from the bottom is gone, I can plug in 0 for h. I can plug in 0 for h in this expression. This piece will go away. This piece will become a plus 0 squared. So I'll get negative 8a divided by a squared times a plus 0 quantity squared, which is negative 8a over a squared times a squared is a to the 4. And negative 8a over a to the 4, you can cancel one of the a's, is negative 8 over a cubed. So this is s primed of a, which is v of a. I'll hold here for just a second. Anybody writing? No.
Why did you move the a to the denominator? So it's a cubed. Or wait, oh, sorry, you subtracted it. Okay.
So these guys multiply to a to the 4, and then this a right here and this a to the 4 can cancel. Yeah.
Okay,
so
okay, thank you. Yeah, I see that now. Thanks.
Oh, no problem. So there's a few power rules for exponents that we'll use all the time, and one of them is this. So we can think of a to the 1 over a to the 4 as a to the 1 minus 4, which is a to the negative 3. Really here, I think the easier way to think of it is that this is negative 8a over a times a cubed. A to the 4 is a times a cubed, so I cancel these guys. So this is all just stuff on the side, not part of the calculation really. All right. So having done all this work, we can come back and say, all right, I now know what s primed of a is. S primed of a, after a fair amount of work, turns out to be negative 8 over a cubed. So I'll copy that down here. And they wanted a few specific velocities. So let me recap on the side here. We found that the velocity at time a is negative 8 over a cubed. And this is the first thing they asked for, right? The velocity at time t equals a. The other things they asked for can all be found by plugging values in for a here. So v of 1 is negative 8 over 1 cubed, which is negative 8. So if we look at the moment here, when t is equal to 1, homeboy is running to the left at 8 meters per second. Running to the left, that's the negative, tells me he's running in the negative direction. And the 8 is the speed. So he's running to the left at 8 meters per second. At time t equals 2, I plug in 2 for t. I get negative 8 over 2 cubed. 2 cubed is 8. This is negative 8 over positive 8, or negative 1 meter per second. So like we said from the graph, he's slowing down. At time t equals 1, he's running at 8 meters per second. At time t equals 2, he's running at 1 meter per second. And then we can look at time t equals 3. V of 3 would be negative 8 over 3 cubed, which is negative 8 over 27. And there are no common factors there. 8 and 27 are coprime. But you can get a feel for about how big this is. This is pretty close to 1/3, right? 9/27 would be 1/3. So his speeds are 8, 1, and 1/3. So he is slowing down, right? He's going fast to the left here, less fast to the left, and less fast to the left. So this is a good problem, good practice with calculation. And also the interpretation here, right? The concepts are important.
I have a quick question on the calculation part. Sorry. On the left side, right there, yeah, the second line down, where did the 4a squared come on the numerator and then the a squared at the bottom? Yeah, right there.
So I know to subtract these fractions, I need to have the same denominator, right?
Yes.
This guy's denominator is a squared. So this fellow, in order to get that factor in his denominator, needs to be multiplied by a squared over a squared. That's this a squared and this a squared.
Okay, thank you.
And the same sort of thing here, right? In order to get this guy's denominator to match this one, I have to multiply by a plus h squared over a plus h squared, and that's these guys. So the step here, all I did was that common denominator work.
Thank you.
Of course. Other questions on the calculation? All right, then I do want to go ahead and show you guys the new stuff for today, right? So those are a few homework questions today. Today we're beginning chapter 3. Which is on differentiation rules. So Robert, I'd be willing to bet that the things you discovered or you've been like starting to notice, those easier ways to differentiate, should be confirmed here. And I'll be excited to see if they are. I'm sorry?
I'm thinking so, because the way you just did it there, and like those 12 steps, I did it like 3.
All right, cool. So there's a few things I want to, first let me draw your attention to the textbook. We're gonna have to move quickly here because we did spend a meaningful amount of time on homework. So I would like you guys to consider reading 3.1 as an obligation, right? You need to get in here and read section 3.1. I'm gonna prove these rules for you today, but we're gonna have to move fast. So first, 3.1 on the power rule and derivatives of e to the x. The power rule look at a few examples. If I want to take the derivative so this, I shouldn't say this is the power rule. Yeah, I'll state the power rule in a second. Just look at a few examples first. If f of x equals c is a constant function, then f primed of x is the limit as h goes to 0, f of x plus h minus f of x all over h. But a constant function f of x equals c, f of x plus h is c, f of x is c, so this is c minus c over h, which is 0 over h. This is lim h to 0, 0 over h. And since this is always 0, you get lim h to 0 of the constant function 0 in here, which is 0. Another way to think of this is that the graph of a constant function is a horizontal line. Here's my x-axis, here's this guy. So the slope is always 0, no matter where you look. So indeed, the derivative of a constant function is 0. And you can get there by a raw calculation like this. Or you can get there by thinking about the graph like this.
I'm sorry, but is that f of x is equal to c or 0?
C. If f of x equal to c is a constant function, so c is the constant here, then f primed is 0. So the derivative of the constant is 0. If f of x is equal to x, then f primed of x is the limit as h goes to 0, f of x plus h minus f of x all over h, the same definition. But now I'm going to plug in the function f of x equals x. So I get limit h goes to 0. F of x plus h is just x plus h. And f of x is just x. So this would give me lim h to 0. The x's cancel and you get just h over h. The h's cancel here and you just get 1. So this is the limit as h goes to 0 of the constant 1, which is 1. I'm going to do a couple more quick examples here. If f of x is equal to x squared, then f primed is the limit as h goes to 0, f of x plus h minus f of x all over h, right? The same definition, which is lim h to 0 of x plus h quantity squared minus x squared over h. We've done this in many calculations like it, so you know how to do this. We FOIL that out, and you get lim h to 0, x squared plus 2xh plus h squared minus x squared all over h. The x squareds eat each other up, and you end up with lim h to 0, 2xh plus h squared over h. And you can factor out an h. Get these canceling. So as we send h to 0, and what's left, which is just 2x plus h, you get 2x. So far, and I'm going to take the opportunity now to introduce some notation. We've seen that the derivative of the constant function is 0. The derivative of x to the 1 is 1. The derivative of x squared is 2x. And you can think of this as 1 times x to the 0, right? So you start to notice a pattern. If f of x or equal to x cubed. So maybe if f of x were x cubed, the pattern would continue and we would get f primed of x as 3 times x to the 2. And in general, maybe if f of x is x to the p, where p is some power, then f primed of x would follow from this same pattern. Maybe this would be that power times x to that power minus 1. This is called the power rule, and it is true. And I'm going to prove it to you. But before I do this, before I go through this proof, I want to take the opportunity to introduce some notation. So you guys remember the delta notation from last week? We talked about like the change in y over the change in x. There's a more convenient way of writing this. Yeah, you notice this takes up a little bit of space. So before I prove the power rule, I'll prove the power rule and then introduce the notation. So first, questions on what it is we're conjecturing here, why we think this might be true.
So
here, if you were to say like 4x raised to something, or f of x is equal to 4x raised to 2, for example, is there a way where we can like easily just add that into this?
There is. Yep. Okay. Yeah. So there's another rule, and I'll prove that for you as well, that says constant multiples just come along for the ride. So let me go ahead and jump to the theorem. There was another question. Sorry, before I
have another question. So say it's like 4x cubed over 3x. We still have to solve for like the lowest power of x, right? And then in order to use this?
In order to use the power rule on something like that, you would need to write the whole function as a power function. We'll address those on Wednesday. What you're getting close to there is something called the quotient rule. And there's a rule for more complicated fractions that can't be simplified. But for now, I'm just interested in power functions. There are rules for dealing with fractions of functions. The one that you described there as your particular example could be simplified to a power function. And then we could use this rule. But there are other fractions of functions that can't be simplified to a power function. And for those, we'll need something else.
All right, thank you.
Of course. Was there somebody else asking a question? Did I miss one?
Just want to say that is what I think I found.
Cool, cool. Isn't that a good feeling? I like this shit. The hair on my arm stands up when you say that because I know how good that fucking feels. When you're like, oh, I think I found something here, and then it gets verified. I'm really happy for you, Rob. All right, let's do this shit. So here's the thing we suspect, right? Having done all these calculations by hand, we have a strong suspicion that the following is true. If f of x is a power function, x to the p, then f primed of x is p times x to the p minus 1. So the power goes down by 1, and the old power becomes a multiple. Right? The way people normally think of this is you bring the power down front, and then you reduce the power by 1. Proof. We will need the binomial theorem. What the binomial theorem says is how you can expand a quantity like this, x plus h all raised to the p. This is called a binomial, and it's being raised to a power. The official statement here is this would be the sum from k equals 0 to p choose k. These are called binomial coefficients. You may have seen them in statistics. P choose k times x to the p minus k, we'll write it like this, times h to the k. Now that looks scary as shit. I'm aware of that. You guys aren't super familiar, comfortable with sigma notation. I'm going to write out what this is, and then I'm going to show you just the first few terms. So this would be p choose 0, x to the p, plus p choose 1, x to the p minus 1 times h, plus p choose 2, x to the p minus 2 times h squared, and on and on and on, all the way down to p choose p times h to the p. The things out here are called binomial coefficients. Calculating them is a little bit complicated. It's done in terms of what are called factorials. I'm going to show you guys what the first few terms of this and the last term of it look like explicitly, and we'll use it like that so we don't have to burn time on this. P choose 0 is 1. So this first term is just x to the p. P choose 1 is p. So this is p times x to the p minus 1 times h. And you see this piece looking relevant. P choose 2 is p times p minus 1 over 2. So that next term is that times x to the p minus 2 h squared. And every other term in here has h's in it. This last term is h to the p. P choose p is also 1. Now, if f of x, if f of x is x to the p, if f of x equals x to the p, then f primed of x has to be the limit as h goes to 0, f of x plus h minus f of x all over h, which is the limit as h goes to 0 of f of x plus h is x plus h to the p, minus f of x itself is just x to the p, and h downstairs is h downstairs. And it's in this line where I'm going to use my binomial theorem. My binomial theorem, the form I will use it is this is equal to this shit. All right, so my x plus h to the p on that bottom line is going to be replaced by the highlighter expression above. It's going to get a little messy, but I promise you we can handle it. It's not too scary. This will be lim h to 0. X plus h all to the p is x to the p plus p times x to the p minus 1 h plus p times p minus 1 over 2 x to the p minus 2 h squared plus lower order terms down to h to the p. From this, we subtract still x to the p, and all of this being divided still by h. The x to the p's eat each other up, just like they always do, right? In every single one of these calculations that you've done, the lead terms eat each other up. What's left is the limit as h goes to 0 of p x to the p minus 1 times h plus p times p minus 1 over 2 x to the p minus 2 times h squared, plus every other term in here has a power of h in it. Terms with h, and that last term is h to the p. All of this still being divided by h. So this guy has an h. This guy has an h squared. All the shit hiding in the dot dot dots have large powers of h, and this very last term has h to the p. So when we factor an h out from the top here, that is our next move. I'll have lim h to 0 h times p x to the p minus 1 plus p times p minus 1 over 2 x to the p minus 2. When you factor an h out there, there will still just be an h, because that was an h squared, plus terms with h in them, right? This next term is like h cubed, and then h to the 4, and then h to the 5. When you factor an h out, these will still have h's in them. And this very last term is now going to be h to the p minus 1. And it's all being divided still by h. And now you can cancel. You cancel this h out front with this h down below. And what is left here is lim h to 0 p times x to the p minus 1 plus p times p minus 1 over 2 x to the p minus 2 times h plus terms with h plus h to the p minus 1. Right, just the stuff that was in the brackets in the line above. But now this piece is going to go to 0. All of these are going to go to 0. This is going to go to 0 because they all have h's. I'm sending h to 0. So the only term that survives is p times x to the p minus 1, and that proves the theorem. Right, this is being multiplied. So this times 0 is 0. All the other terms in here, they have mixtures of x's and h's and p's, but they all have a factor of h. So they all go to 0. And this last guy is just a pure term of h. He's of course going to go to 0. So the only term that survives is this guy. So the derivative of the function x to the p really is p times x to the p minus 1. This is it. This is the whole proof. It's a consequence of the binomial theorem. So we do need to know the binomial theorem. That's why we teach the binomial theorem in pre-calc. Yeah, Robert?
Are you going to have us prove this in a test?
I can't quite hear you. What was that?
Are you going to have us prove this on a test?
No, you won't have to prove this on a test. You will be free to use this. Just the result. I do want to prove one other thing for you real quick, and then we can do some examples. Make sure I'm still doing good on time. Yeah, all right. So that's the result, right? Is that if f of x equals x to the p, then the derivative f primed is p times x to the p minus 1. I got one more theorem for you. So f of x equals x to the p implies f primed of x equals p x to the p minus 1. This next result says two things. Call it capital F of x is equal to little f of x plus little g of x, then capital F primed is little f primed of x plus little g primed of x. So if you want to take a derivative of a sum, you can just differentiate each piece on its own. And the derivative, if capital G of x is equal to a constant times little g of x, then g primed of x is c times little g primed of x. So derivatives play nice with addition, and they play nice with multiplication by constants. The proof here, maybe I'll hold off on. The proof here is not hard. We'll say it's an exercise. You can read it in the textbook. It's not a hard proof, but I want to work examples. I think that's how you guys will understand this stuff best. So let's work an example. So let's find the derivatives of f of x equals x to the 7, g of x equals 2x cubed minus 4x to the 5, and h of x equals 3 minus 5 times 1 over x squared. We have our power rule now. So I know how to differentiate power functions. And what the theorem above here is telling you is that derivatives split up nicely over addition and constant multiplication. This is a 5. Yeah, this is also a 5. No S's, all 5s. Okay. So f primed, I just use my power rule. P here is 7. So I bring the power down, and then I'll have x to the 7 minus 1, which is 6. Is everybody comfortable with this first one? Just straight application of the power rule. If f of x is x to some power, then f primed is that power times x to that power minus 1. All right, let's look at the next guy. Here, g primed, I differentiate this, and I differentiate this separately. So this is going to be, well, I'll break this out schematically. This is 2x cubed primed, and the prime here means we're going to take the derivative of this. This is the same as plus -4 times x to the 5, and I need to prime that also. So really, this is what that second theorem is telling us, is that you can split up derivatives over addition or subtraction. So I'm thinking of this as a function plus this as another function, and I need to take the derivative of each of those. Now, according to this rule up here, the 2 out front should pop out. So this will be 2 times x cubed primed, and this -4 will pop out. So I'll have minus 4 times x to the 5th primed. And again, this prime notation means we need to take the derivative. So x cubed primed, the 2 comes along for the ride, and here we will get 3x squared. We bring down the power and we reduce the power by 1. Then I'll have minus 4 times the derivative of x to the 5, which is 5x to the 4. And we can clean this up. This is 6x squared minus 20x to the 4. Isn't this so much nicer than that limit definition? Can you imagine crunching out that limit definition for x to the 7, or this combination 2x cubed minus 4x to the 5? It would be horrible. The challenge here is the notation. I think the rules are pretty simple, but the notation might take a little getting used to. Before I move on to that last guy, h of x, are there questions about f or g here? Questions about the symbols I'm using?
I have a quick question. For the last one, is there, I mean, this might not like be beneficial at all, but would you be able to like factor out the x squared, or like do you do that at all in the last one? Like the last part?
When you say the last one, you mean h of x or g of x? The one we just did?
Yeah,
Or
just the last step for g of x.
here, you could factor an x squared. Yeah, actually, you could factor a 2x squared out if you wanted to. And there are plenty of moments where that will be a useful thing to do. For now, I'm just concerned about calculating the derivative. But later, if you wanted to find out where this function is increasing, decreasing, all that sort of stuff, it turns out that factoring your derivative is the game there. So that will be important.
Okay, thank you.
Of course. All right, let's take a look at this last example here. I'll do him on a separate page. And then there's one last bit of notation I want to introduce after here too. So h of x before I take my derivative here, I'm going to rewrite it. I'm going to rewrite this function. This is 3 minus 5 times 1 over x squared. That's x to the negative 2. So now h primed of x will be the derivative of 3 plus the derivative of negative 5x to the negative 2, like this, just like we did on the last one. Everybody with me so far? What's the derivative of 3? What's the derivative of the constant function 3?
0.
Good. 0. Now the negative 5 is going to pop out of this guy. And I need to differentiate x to the negative 2. That's
Why is 3 0?
The derivative of 3 is 0 because 3 is a constant function. If you
okay.
think about this function on its own, right? It's the graph y equals 3 is a horizontal line. Its slope is always 0.
Okay.
And then here, what is my derivative? So I pop out the negative 5. All right, this is negative 5 times the derivative of x to the negative 2. And then the x to the negative 2, that also follows from the power rule. So this will be 0 minus 5 times negative 2 x to the negative 3. I bring the power down and I subtract 1 from the power. Same shit. It works great, even if the power is negative. In fact, it works great even if the power isn't a whole number. It works really well for any power. It's a nice fact. So what we end up here is, I'm not going to write the 0 anymore, minus 5 times negative 2, that's positive 10 x to the negative 3. Or if you wanted to, you could write this as 10 over x cubed. Okay. So the power rule is not super hard to work with. It's actually really nice. If there's like one differentiation trick that everybody seems to remember after Calc 1, it's the power rule, which is good because it's probably the most useful one. I want to, in these last few minutes here, share with you a little bit of notation. The prime notation is good, but there's another notation for derivatives. Stuff primed can also be written as d dx of stuff. These mean the same thing. And f primed of x can also be written as df dx. This was the like having a bunch of different words for snow comment that I made last week. Mathematicians have a bunch of different notation for the derivative because it's something we are constantly immersed in, and different notations are better at expressing different concepts. So I'd like to share with you the derivative rules that we learned today. The notation over here with the d and the dx, this is called Leibniz notation, named after Gottfried Wilhelm Leibniz, one of the discoverers of calculus. We discovered that d dx of x to the p is p times x to the p minus 1. This is the same thing that we said earlier, right? D dx, the derivative of x to the p, which is the same thing as saying I want to prime x to the p, is p times x to the p minus 1. We discovered that the derivative of a constant function is always 0. And then here's a nice mixture of the notations. We discovered that the derivative d dx of a sum of two functions, f of x plus or minus g of x, is the sum or difference of the derivatives, f primed of x plus or minus g primed of x. And really there was an extra thing we learned here, and that was that the derivative of a constant times your function is that constant times the derivative of your function. So here's these are the same rules that we wrote down earlier, but they're expressed in this notation, this combination of Leibniz notation and prime notation. You want to get comfy with this. So the object d dx is called a differential operator. This thing, d dx, called a the top says differentiate whatever's over here, and then the bottom says with respect to the variable x. It says differentiate whatever's next to me, treating the thing that I have down here as the variable. So the differential operator notation, aka Leibniz notation, has the advantage of being able to be interpreted as a rate of change. Like the top here is a change in y values, and the bottom here is a change in x values. We use the d instead of the delta. Remember the delta from last week? Delta y over delta x? Well, the d is kind of the infinitesimal version of the delta. It means infinitely small change. I wouldn't stress too much about the meaning of df or the meaning of dx on their own. They are called differentials. We will talk a tiny bit about them at the end of class. For now, what I want you to think of is d dx says just differentiate whatever is next to me. Differentiate whatever is over here with respect to the variable x, meaning think about whatever this symbol is here as the variable. And these, again, are the same rules that we discovered earlier, just expressed in that notation. Okay, this is exactly where we wanted to leave off, and we are right at time for the class. So I am going to go ahead and end the lecture here. I encourage you guys to go back and look at the textbook again. So please, please look through section 3.1. They have alternate proofs, right? Like here's the proof that we did of the power rule. They have an alternate proof here based on the alternate definition of the derivative. And they have lots and lots and lots of examples that we haven't had time to look at. So on Wednesday, I will come in here and start working more examples. We did like this guy, but we haven't done anything like this guy. And then we're also going to discover how to differentiate. Here's the constant multiple rule and the sum rule. They've got the proofs of those in here, which is good. So please read section 3.1, at least up to here. So read section 3.1, at least up to example 5 or example 6. And next time we will pick it up here at exponential functions. Okay, this is where we're going to go next time. So I would love to spend more time on this stuff with you guys, but unfortunately this is just all the time we have. So please, please, please read section 3.1, and then and we will pick it up at the bit on exponential functions on Wednesday. Also watch out, there's going to be a new homework dropping a little bit later today. It's not out just yet, but it will be out around 12:31. Any urgent questions before we sign out for the day? Okay, I hope you guys have a lovely rest of your day. Again, please read section 3.1, and I will see you next time.